Bismillahirrahmanirrahim. Greetings. The contents of this video lecture is continuation of the previous lecture, in which we are trying to prove analytically the existence of a number x such that x squared equals to 2. Now, the emphasis of our proof, previous lecture and also this lecture, will be on the set S, that we defined it to be the set of all positive rationals such that x squared of them is less than 2. Now, I would like to say a few words aside before we start the proof, and something that I should have possibly mentioned it in the previous lecture, and that is about the motive of selecting such a set S. What was the motive behind that? Okay, then let me zoom this one, and I have the thing written for us, and I stay out of way and we lecture it. May I do that, please? Okay, as I have said here, I've written that we want to know the motive behind selecting this set. And we know what that set is. It's the same set that we talked about in the previous lecture. Now, the first one is this. I've written, I think, 3 or 4. Now, according to the Pythagorean theorem that we are all familiar with, a squared plus b squared equal to c squared, if a equals to 1 and b equals to 1, then c squared will be 2. So we know there is a number that the square of that is 2 according to the Pythagorean theorem, but what is that number we know is not rational. You follow me? This was known for thousands of years ago about that. Okay, then second motive that we have for the selection this set is that if a number x is neither less than 2 nor larger than 2, then what? Then that number must be 2. Is that right? That is our second, in a sense, motivation of selecting this set. Now the third one is that proof by contradiction. I've gone deep into that in the previous lectures. Whenever we have difficulty to prove something directly, we have 2 other options. One of them is proof by contradiction, and the other one is proof by counterpositive. If P, then Q. If not Q, then not P. Sometimes also come to our rescue to solve a theorem or whatever that is a bit difficult to prove directly. So that is the above. That is our third kind of motive of selecting this set. And the fourth one, which is more interesting, is that we are really cheating. We already know about the square root of 2. We know the decimal expansion of that. There is no pattern of repetition. We know all of this together. This goes forever. So I made a sequence out of this, and then we discussed about the sequence and what that sequence has to do with this one. Look what happened. The sequence I made is 1, which is the first digit of this one, of this long. Then next one is 1.4. Next one is 1.41. Next one is 1.41, I didn't write it, huh? No. Next one is 1.144, 1.4142. Then next one is 1.4143, and so on and so forth, goes forever. Now, the point is that every element in this set, we can call it set in fact, satisfies the definition of set. Every element in this set or in this sequence is what, if we square it, is less than 2. Do you follow me? Of course, this sequence will converge, but that is a different story. So this is our other motive for selecting this set, to emphasize and go through the proof of by contradiction that the existence of such a number x such that x squared is equal to 2. Okay, I hope you are clear with that, huh? Now let me go to the next. Then let me start the proof, in fact. I apologize for the primitive equipment I have. Aye. But I'm conveying the message, the knowledge, anyhow. Maybe even better. Now, our assumption is, suppose that L squared is bigger than 2. Is that right? And we know what L is. It's the same L as we discussed it in the previous lecture. It's the supremum of our set S. Now, we know that L minus 1n should be in the set of S. That means L minus 1L squared should be what? Should be less than 2. Do you follow me? Now, based on this assumption, as a matter of fact, we end up to be this to be greater than 2. And that is what contradiction comes from. Do you follow me? Okay. Now, we go ahead and we start with this one. We expand it. Is that right? Then next one is what? Next one is I take this one out. If I take this one out, the remaining two terms, which is this, definitely is less than this, because I took a positive term out of these three terms. So these two terms will be less than this. Do you follow me? Now, what I do, I make even the inequality stronger, which means I add a negative terms in that. Do you follow me? If I add the negative terms to these two terms, this becomes even much smaller than this. And then when we simplify, we end up with this algebraic expression. And we are very familiar with that. Now, again, as I have mentioned in the previous lecture, we concentrated on this. If we can replace this one by what? By 2 minus L squared, taking under consideration that we are preserving our inequality, then we are in business. We have achieved our goal. So let's see now what we can do. Now to do that, it goes to the Archimedean properties. Now, L squared is bigger than 2. That is our assumption, is that right? Therefore, L squared minus 2 is a positive number. And then 2L plus 1 is also a positive number. We know why, huh? And that, according to the Archimedean theorem or lemma or a property, there exists a natural number n such that when we multiply by one of them, which is in this one, will exceed the other one. So this is our x and y that we discussed it in the previous lectures about Archimedean property. So we know that one. So we do that, such an n exists, and then we divide both sides by n, and this ends up to be 2L plus 1 over n. And then if we multiply both sides by negative, then this becomes larger than that. Do you follow? Right now this is bigger than that. So let me do that one in the next lecture. Okay. Now, what I just said, I'm doing that. Now I divide both sides by n, end up with this one. Now, what we do, we multiply both sides by negative, then becomes 2 minus L squared is less than this. Because in the previous one, this is what we concentrated, that's what we needed. So, in other words, this is larger than this. Is that right? You see that? Even though this is negative, but it's larger than this. So, if we replace this one by this, then what happens, which is smaller than that, then we have guarantee for preserving our inequality. That's exactly what I did. So starting from that, I replaced this one by what? By 2 minus L. And when I did that, L square and L square, they cancel each other, so we end up with L minus 1 over N square is greater than 2. And that is absurd. Now let me put all of them in one line for you. That I have done it, I have put them writing here, so that, because I'm not on the board to continue, so they were kind of a little bit maybe off. And I may need that one. So I'm just going over the same thing again, but a little bit in a kind of chain, algebraic chain. So we started with L minus 1 over N square, and we end up with algebraic expression L square minus 2L over N plus 1 over N square. And then we know that this is what larger than this, or we can say this is smaller than this, all right? And then we add another term which is negative, which means we made it even smaller, so that we have guarantee we are preserving our inequality. Then we end up with this, is that right? Then we simplify. Now, we have in mind, we think about, okay, if we succeed to replace this one by 2 minus L square, then we are in business. Because L square and L square, they cancel each other, we end up with 2, and that is what contradiction comes from. So to do that one, we went what? We went through the Archimedean property, and we succeeded to do that one. Okay, then, looks like we have come to the contradiction. Now, let me just put the last one, and I put up one more time. I go over that, and that is the last part of it, and that is what we have succeeded to demonstrate that L square less than 2 and L square greater than 2 leads to contradiction. Both of them lead to contradiction. So if a number is neither less than 2 nor greater than 2, that number must be equal to 2. Do you follow me? So the conclusion will be is that there is a number x such that x squared equals to 2. The existence of that is proven. Okay, then let me zoom this one back. Now, the only thing is left that a curious student may ask is to show that how do you know that L square equals to 2 is unique? The uniqueness comes into the picture. And that is very simple. Suppose there are two, L1 and L2. L1 square equals to 2, and L2 square is also equal to 2. Since 2 equals to 2, that means L1 equals to L2. Do you follow me? Or we can use the transitive property of equality. L1 equals to 2. 2 equals to L2, and then that means L1 equals to L2. I don't have to write it, do I? Let me repeat one more time. L1 equals to 2. Suppose there are two of them, L1 and L2. Then 2 equals to L2, because both of them are equal to 2. That means by transitive property of equality, L1 equals to L2. So that answers the question of uniqueness. Okay, then, I hope that this lecture and the previous one are productive and you learn from them. And I hope that all my channels, if you have noticed that my style and method of teaching a little bit different. I emphasize about critical thinking, and I dive deep into the subject, and I do not accept any kind of memorization or recipe following. Okay, then again, as always, at the end of the lecture, I mention if you have any comment or if you have any suggestion or if you find any error in any of my lecture, please bring it to my attention. Feel free to write it in the comment section below, and you will be doing me a great favor. And there is always room for enhancement for teaching, so please, if you have any comment how I could do this and not do that, and that will also help me for applying them as a better teacher. Okay, then again and again, I thank you for watching my videos. I wish you all prosperity and good health and happiness, and please stay and remain safe. So long.